Hello everybody, welcome to the first episode in my devlog series. Over the course of this series, I'm going to be creating a Minecraft minigame server like Hypixel, starting from scratch. And I'm going to be sharing my journey with you guys here on YouTube. So here in this first devlog, I kind of just want to talk about my plan for the project, where I want to go with it, and some of the stuff I've learned about how servers like Hypixel run their networks. Now, I do apologize, this first devlog is going to be very technical. I really want to focus on the solution I've made, which I'll talk about in a little bit. So if you're not a fan of technical devlogs, this one probably isn't for you. But in future, I'm also going to do a couple more videos focused on the design. Like I think the next one, I kind of have an idea for the first minigame I want to create, and I talk more about that in the next video. But this one is going to be very focused on the technical and exactly how my solution for running a server network works. So the first thing I kind of wanted to figure out is, how do big servers do it? How do server networks like Hypixel, and even, I know nobody plays there anymore, but even Mineplex, you know, we all played on Mineplex at one point, how they manage their servers and how they create a seamless experience for hundreds of thousands of players to play concurrently. It's very seamless, it's very nice for the user, and I was very curious on how the servers managed to accomplish this, especially with Minecraft's extremely limiting server technology, which is really kind of a pain, and you have to use third-party software. And even for small SMPs, like with your friends, you're gonna need to use third-party software, otherwise your performance is gonna be completely abysmal, and it's gonna be a struggle to play without lag. So it took a bit of digging, because there isn't really much information on the internet about how servers like Hypixel work. But I managed to find some old threads and things on Hypixel forums and around other parts of the internet that kind of gave me an idea of how these servers, Hypixel in particular, manage their server networks. Basically how they do it is they create containers with their server software, and if you don't know what a container is, don't worry, I'll explain in a minute. They create containers with their server software, and they dynamically allocate those using a service like Kubernetes or some other kind of container manager. Hypixel has a whole bunch of different servers that they mesh all together with a proxy. Now, I'm sure a lot of us have seen this kind of thing before. We've all probably set up a bungee cord server at some point, or played on a network with a few servers connected together, and usually you just have one main server and then like a couple other servers that players can join when they want to. But it seems like Hypixel is actually doing something a bit bigger. Because they have so many players, this all needs to happen extremely fast, and it would be a huge waste of money to have all these servers going all the time. So it seems like what they do is they dynamically create and destroy servers while players are playing. Essentially what that means is that Hypixel always has the right amount of servers, so they're never paying for extra servers or having moments where players can't play because those servers are full. And I kind of wanted to recreate that with my own technology, and I think I found a way to do it using three quite incredible pieces of tech. One of them is Docker, the other one is Kubernetes, and the third one is RabbitMQ. Now I'll explain what all three of these things are in a second, but basically what you have to know, I found a way to use these in a way that allows us to do essentially the same thing as Hypixel. Now, starting off with Docker, basically what Docker allows you to do is it allows you to put your application, so in this case our Minecraft server, into a container, and that container is kind of like a little box that has everything that application, so our Minecraft server, that has everything that Minecraft server needs to run. So it has Java, it has all those things all packaged up in a nice little box. And what this means is that you can go to any computer anywhere, no matter if it's Linux, if it's Windows, if it's Mac OS, if it's, you know, a Raspberry Pi or a desktop, it doesn't matter what it is. You can do a simple little Docker command, and Docker will pull that container from the cloud with your application in it, so with our Minecraft server in it, and run it. So you don't have to worry about installing Java, you don't have to worry about anything. Everything just works no matter where you are. And this is really powerful because it allows us to use another service called Kubernetes. And what Kubernetes does is essentially manage a whole bunch of these Docker containers. So what we can do is use this to dynamically create and destroy our Docker containers. Now, Kubernetes can be a bit more complicated than that, but that's all we really need it for in this scenario, because what we wanted to accomplish was to have servers that can be created and destroyed as players need them. And what Kubernetes allows us to do is do that with our Docker containers. So our process can be package the server application into a Docker container and then use Kubernetes to create and destroy them as we need them. Now, the third piece of the puzzle here is not as important as the other ones, because really a lot of different applications could do this, and there's 100,000 different ways that we could have this work. But the question is, how do we have all these little containers talk to each other? And that is where RabbitMQ comes in. Now, RabbitMQ is a messaging queue server. Essentially what that means is your applications can send and receive messages through RabbitMQ. This can work as our messenger between all the servers. So let's say we have a lobby server and 10 players on that server want to play Bed Wars. So they click on the NPC, and on the back end, that server says to the RabbitMQ server, hey, I have 10 players that are looking for a Bed Wars game. And then what we can do is we can have some kind of matchmaking service, and that can read those messages from the lobby server on RabbitMQ, and it can go, hey, 10 players want to play Bed Wars. Okay, well, we can fit 5 players in each Bed Wars lobby, so we're going to need 2 Bed Wars lobbies. And then it can create 2 Bed Wars lobbies, and then those Bed Wars servers can look at the RabbitMQ server, say, hey, these 5 players want to play here, these 5 players want to play here, and we can connect everyone to those 2 servers, and it all works. So essentially, RabbitMQ is acting as the messenger between the servers to keep everything connected. Now, this isn't the only way we could have done that. I could have done it in many different ways, but this seemed like a good option because RabbitMQ is event-based, and it's also extremely stable, so it doesn't really crash. It's very, very reliable. I'm making this video kind of as a follow-up to the first devlog. A lot of people had questions about how exactly my whole system works, so I thought I'd just make a kind of devlog 1.5, and I'm just going to go through all the code step by step and explain how everything works. So if you're interested in that, this video is definitely for you. I'm going to explain how everything works. I'm going to show you all the Kubernetes stuff, all of the RabbitMQ stuff, all of the Docker stuff, how it all works, how it's all set up, and all of the code and everything behind it. All right, let's get into it. So here we are on the server, and this is running on Kubernetes right now. So this lobby server and the proxy are both running inside of Kubernetes. Basically, the proxy just has a load balancer that's giving it an external IP to connect to. Now what we're going to do is we're just going to go over to our NPC, and if we click him, it should say starting search for Void Rush, which is just the name of the minigame I'm working on. I'll talk about that more in the next video, but so basically what that's done is it sent a message on RabbitMQ. It should be creating the server, and once it's done, it should connect us to the server all through Kubernetes, all through RabbitMQ, all done automatically. And yeah, there we go. Let's connect this to our game server. Here we are, and if I just start the game, everything should work. We can play. Game doesn't work yet, but basically that's it. That's how it works. So now I'm going to actually go through and explain what all just happened. Okay, so the very first thing that happens is we use a Kubernetes command to deploy a pod with this proxy server running in it. This is a Velocity proxy. I've just written a custom plugin for it that kind of manages all of the Kubernetes stuff, all the Docker stuff. The very first thing that happens is the proxy initializes all the default Velocity proxy stuff, gets booted up, and then it loads our plugin. So this plugin, the very first thing it does is it initializes a RabbitMQ connection right here. So basically it's just creating a connection to the RabbitMQ server. Then the next thing it does is it starts consuming messages from that server. So these 3 lines here all start consuming on a different channel. So this first channel here just consumes server declares. And basically what that means is it's listening on the RabbitMQ server for every time a server sends a message to that queue saying, here I am, this is my IP, I need players to be able to connect. The next line is listening for player joins. I think I should actually rename that because that's not really what it does, but basically what it's doing is it's listening on the player join queue, which is actually a matchmaking queue. The proxy doesn't have that NPC, the lobby server does. So when we click on that join NPC, it has to send a message to the RabbitMQ server, and then this proxy consumes that message because the matchmaking is all happening on this proxy server rather than the lobby servers. So that's all that's doing. It's just listening for when the player clicks on one of those NPCs. And then the third and final message consume line there is just a simple channel that I have set up so I can publish messages to that and it'll shut down all of the Kubernetes pods. That's just more for debugging and testing because it's really annoying to have to manually shut down each pod individually. So I've just created a simple way of shutting them all down at once. The next 4 lines, the only important one is the spin up lobby servers because the rest of them are just registering commands and events and other basic plugin stuff that's really not important to this explanation. So let's take a look at what that spin up lobby servers function does. So here we are. Anything with logger, it's just outputting a message to the console. So I can kind of see what's going on. It's just for debugging. But essentially what it's doing here is it's creating the lobby servers. So it just loops a certain number of times. I have this only set to 1 because right now I only need 1 lobby server, but I could set this to anything
So if I set this lobby servers variable to like 10, then it would loop 10 times and create 10 lobby servers. But where it's actually creating the server is in this server manager.create lobby server function. So let's take a look at that. And here we have the real kind of code behind creating the lobby server. So on these first few lines, we're just creating all the variables we need for accessing Kubernetes. That first one is just creating a API client. The next line basically just says set the Kubernetes cluster configuration for that client to be the current Kubernetes cluster that the application is running in. So it's just saying basically the current Kubernetes cluster. And then the next thing that's kind of important is this block here. And what that's doing is it is creating all the variables that we're going to need for our pod, and it assigns some environment variables that we'll use later on the actual servers running inside those pods to set some data that we need to know, like that pod IP. We're going to need to know that so we can actually connect players through the proxy. Yeah, so then we create the container object with all of that data. We create the pod, and then we just use the API to create that pod inside the Kubernetes cluster. And that final line there is just adding the lobby's UUID, which is part of the metadata, just so the server can be identified. Right now, I'm just using the name of the pod. I think that's not really the best way. I gotta find out a better way to do this, but right now it just creates a random UUID and then calls that pod lobby.theUUID, and then I can just read it from that. But I think there's probably a better way to do that. So if anyone knows a better way to do that, that'd be super helpful if you could let me know in the comments. Anyway, that last line there is just adding that lobby UUID into a list of lobby servers just to keep track of it. It'll be more important later when we're deciding what server to connect players to. So that's kind of everything that happens when I start up the proxy. It will create a lobby server. It sends a message to RabbitMQ once the lobby server is actually started, and then it'll register that server on the proxy so players can actually connect. The next thing that happens is with the actual minigame. So when we click that NPC, we do some basic matchmaking stuff. It's really nothing too fancy right now. It just has a big list of players. When there's enough players in that list, it'll just divide it into the amount of players it needs, and then it will send them into a game server. Creating the game server works exactly the same way as the lobby server. It just spins up a server. Then when that server comes online, or it sends a message to RabbitMQ with its UUID and everything, and then we just register that server and connect players to the server. So that's pretty much the whole system. It's very kind of beta right now. I haven't really stress tested it at all, or I'm not even sure if it works under real scenarios. The only thing I've tried is with like 1 or 2 players trying to connect, and it works right now, but I think there's some big issues with it that I'm gonna have to solve. For example, I don't know if I can actually use the pod IP, because I think Kubernetes might destroy, like, I don't know if Kubernetes guarantees that pod will always be under that IP. Like, I feel like it might destroy it and create a new one. I'm not really sure, but there's all issues I'm gonna have to sort out. But right now, this is the basic system. It's not insanely complicated. It's just, there's a lot of different applications. Like, there's a lot of different places messages have to go. There's a lot of different applications that have to be talked to. There's a lot of different things that have to be coordinated for it to all work. But right now, that's the whole system. Once I kind of improve it, I'll make another update on how exactly it works. But if you're curious on how to do this, this is kind of a little bit of a walkthrough on how my system works and some of the code behind it. So, from survival games to battle box, minigames have long been a part of the Minecraft community. Legendary games like Sky Wars, Bed Wars, and even classics like survival games have defined the minigame landscape. Servers like Hypixel have found incredible success and grown beyond just simple video game servers and into full-scale businesses. These companies employ full-time developers, designers, and artists to craft their minigames. But behind all of this, how does one actually go about designing and creating a minigame? How do they go from ideas in a designer's head to actual playable experiences? Well, that's what we're going to talk about in this video. Hello everybody, welcome back to the devlog. In this one, we're going to be talking about how I have created my very first minigame for the server called Void Rush. But before we start that, I just want to say a huge thank you to everyone who has subscribed. We've just hit 3,000 subscribers, which honestly is incredible to me. Thank you all so much for the support. It's been incredible to hear all of your feedback and your comments and your amazing ideas for the server. In other news, I now have a Discord server, so if you want to talk about plugin development or YouTube or really anything, invite link is in the description if that sounds interesting. All right, let's get into it. So how do you actually create a minigame? Now, I've had some experience with this before. I've created a couple Minecraft
tournaments, I guess, similar to MCC and other projects like that, where I've created custom mini games and had players compete. But I've never created something that's supposed to be standalone. So the original idea for this comes a lot from one of the games I had in one of these tournaments that was also called Void Rush. It's very similar to Bed Wars in a lot of ways, but essentially you have a generator in the middle of the map, and again, like Bed Wars or Sky Wars, it takes place on an island, so players have to bridge between the different areas. And again, just think of a Bed Wars map, very similar to that. You know how you have the emerald generators in the middle? In this one, you have a pile of void ore, and the objective of the game is to be the last team to survive. And how you do that is by collecting void ore. So everything in the game costs void ore. There's upgrades you can buy for your team, which I'll talk about more later. There are void powers, which you can purchase for your team, and you can upgrade those. That's kind of another system I'll talk about later because it's pretty interesting. Functions a bit like a roguelike game where you have kind of different builds you could create every time. How this all works is with void ore. So you collect void ore from the center, and teams can steal void ore from each other by going to another team's island. And if you die with void ore on you, it drops and other players can pick it up. Now, I'll talk about that a bit more later because it actually turns into something called infused void ore, which can be used in a couple different ways. But essentially, the goal of the game is to get void ore. Now, respawning also costs void ore. So every time you die, your team loses void ore. So there's this interesting dynamic where the void ore is not just a way for your team to stay alive. It's like a health bar, you could say, but it's also a currency. So you have to make the trade-off between getting upgrades and becoming more powerful and staying alive, keeping your health pool high. And this is really what I wanted the core mechanic of the game to be, basically having that trade-off between being more powerful as a team or having more health as a team, because you need both to be able to survive. You don't want to go too low in your health because then you'll be easy to take out, whereas you also don't want to have no equipment or powers or anything because you'll be behind everyone else. So another system that's really interesting is the power system. Now this system really takes a lot of inspiration from roguelike games like Hades, for example, has the system where every run you have optional powers that you can pick up, and basically you have a different build for your character every time you run through. So I took a lot of inspiration from systems like that, and essentially you have a whole big pool of void powers, and every game you have a random selection of those powers. Now you can re-roll them by paying void ore. It allows you to kind of create different builds, so you can create really interesting synergies with that. Now there's actually another level to this system called infused void powers, and infused void powers are essentially stronger powers. So I think right now every team can have up to 5 void powers, so the basic powers, and they're little things like getting a bit of extra speed when you take fall damage, or maybe having your arrows go a bit further when you shoot them, or maybe having a bit of like a damage over time effect occasionally if you attack. Generally pretty small things. Definitely noticeable, but small things. The infused void powers are supposed to be much more powerful, so there'll be things like exploding on death, or getting a second chance when you die. Like if you fall in the void, there's one, for example, if you fall in the void, it'll deal a bunch of damage to you and actually boost you out of the void so you won't die. And that can be paired with other powers that maybe allows you to slow down your fall while you're aiming a bow. So there's interesting synergies there as well. These infused void powers are kind of like an upgraded form of multiple void powers mashed together. Basically, it takes lower level powers and stitches them together into more powerful abilities. Now, how you get these powers depends on which one it is. So for the basic void powers, you can get them with just void ore. They'll cost an amount of void ore. Basically, you click on the shop and then you'll get 2 options. Now, none of these have textures yet because I haven't done any kind of art with this yet. It's all just code, so everything looks very primitive. But basically, yeah, you have these 2 powers and you can choose to re-roll them, but that will cost void ore. So if you really don't like your options, you can always get new ones, but usually it's better to take a pick, and then you can choose one, and that just costs void ore. Nothing too fancy, it's just pretty much basic power upgrade. Now with the infused void powers, it's a little bit different. So you actually need infused void ore. So the way to get infused void ore is to kill somebody who has void ore on them. So if a player gets a bunch of void ore, either from stealing it or from mining it from the center, and you kill them, that void ore will drop as infused void ore. Now that infused void ore is worth 2 regular void ore. So if you choose to put that towards your team's regular void ore, which you can do, it'll count for 2. So there's that interesting dynamic of, do I want to use this to get myself an infused void power to get our team more powerful, or do I want to give our team more health and get more void ore? And again, that's coming back to that dynamic of
the choice between the two things and trying to incorporate a bit of dual purpose design as well. Yeah, so if you don't choose to use that fused void ore for team health, then you can instead use it for buying infused void powers. Now that's kind of the whole system with that. I might change it around a little bit. I have to, I really don't know how balanced it is. I might change the values. I might make it so that void ore, infused void ore gives you more, or there's less power slots or stuff like that. And I'm gonna keep trying adding new powers. I think I have about 10 or 11 normal void powers, maybe 5 or 6 infused void powers, but that's something that can really be updated and added later on in the future. How you win is you're the last team alive, and a team is eliminated if they run completely out of void ore, either by dying enough times, because remember, respawning costs void ore, or if no team is being eliminated and it's just going on and on and on. The game only lasts for 12 minutes, so after 12 minutes there will be a death match, and essentially what that means is just every second a certain amount of void ore will be taken away from all the teams, and the last team with any void ore remaining, the last team to be eliminated, will be the winners. So this is kind of just a nice way to bring the game to an end. Now I really wanted to keep the games fairly short because most players usually don't like long games, especially if their team has been eliminated and they just have to sit and watch either their teammates or something else happen or other teams happen. Now usually that's not a problem because they can just queue into a new game, but I wanted to make sure that nobody is in the game doing nothing. I wanted to keep the game fast-paced, keep everyone playing, keep it all going. With that said, that's basically it. This game was really interesting to design. Takes a lot of inspiration from current games on the market, such as, Bed Wars, really the main inspiration behind the kind of Minecraft side of it. Now, a lot of the ideas in this came from this amazing video by Mark Brown on dual purpose design. You've probably heard me mention that through the video. I would absolutely recommend watching it, and all the other videos on his channel is fantastic for game design. Really an amazing way to learn, and extremely high quality videos. Highly recommend go watch that. I'm not sure if the game is in a playable state yet, but it's definitely at a state where it needs to start testing. So I think that I want to do a playtest soon. I'm not sure when it would happen though, but all of that would be shared on the Discord. So if you are interested in playtesting the game, definitely go and join the Discord because I'll put all the information there. And if I do run a playtest, I'll probably announce it with a YouTube community post as well. But majority of it will happen on the Discord, and I'll be giving updates and kind of instructions on the Discord because I guarantee it will not go smoothly. Stuff will break, and I'll do my best to communicate that with the playtesters. Feedback loops are a foundational element of game design, wielding the power to either elevate or ruin a game's core mechanics. When misused, they can pose significant risks to the balance and player engagement. In the case of my game, a few unchecked feedback loops in the core design have caused large rippling issues throughout the rest of the game. Welcome back to the devlog, everyone. In this one, we're going to be talking about feedback loops and how they're important to the core design of my game Void Rush. Okay, so let's start with what actually are feedback loops. Feedback loops are just loops where the output feeds back into the input. These loops are found everywhere, even in science, nature, economics, really any part of the world. But specifically, in our case, they apply to game design. Now, there are two main types of feedback loops, positive and negative. Positive feedback loops are like a snowball effect. Think of a rich get richer type of thing. Negative feedback loops attempt to keep things in balance by redistributing. Now, when you hear positive feedback loop, you might think that the snowball would always be positive. In Call of Duty, for example, when a player kills enough players, they get a kill streak, which helps them kill more players, which gets them more kill streaks to kill even more players, and so on and so on. So they just shoot up the scoreboard, and it means the players who are doing very well do even better, and the players who are doing not so well stay where they are. But there's actually another type of positive feedback loop, and it can be kind of counterintuitive because it's in the negative. Now, I know it's kind of weird to think of a positive feedback loop in the negative, but the positive part of that is just the snowball effect. So this can work in a negative sense too. Let's say, for example, you have a game where every player gets 100 coins, and players can spend those coins on getting upgrades to help get more coins. So the players who start getting coins early are going to get that one positive loop where players who have more coins can buy more upgrades to help them get more coins and more coins, which buy more upgrades, and so on and so forth. But there's actually another type of positive feedback loop that's happening here too, and that's for the players who are losing coins. Say every time you die, you lose 10 coins. Now, the players who are dying are going to lose coins, which means they'll have less money to buy upgrades, which means they'll die more, which means they'll lose even more coins. And again, it kind of sends the whole game into a downward spiral. Now, this type of feedback loop can be really fun for players who are doing well, as they're kind of mopping up the competition. And every time they do better, they keep doing better, and they're just doing better and better and better. But it can also lead to a huge balance issue where players on the bottom end of that scale really aren't having any fun at all and just feel like they're being destroyed by the top players. Now, this can be good for fast-paced or competitive games. However, they're not so much fun in casual games, and done wrong, they can pose a pretty big issue to competitive games as well. So this is where the second type of feedback loop comes in, negative feedback loops. A good example of negative feedback loops is the classic that everyone uses, but Mario Kart. In Mario Kart, the players in first tend to get pretty bad items from the drops, like green shells or bananas or things that just aren't super helpful, while the players in the back of the race are showered with invincibility stars, bullets, blue shells, and other things that help them advance. So this negative feedback loop works a bit more to balance it. So the players in the back will be helped more to push forward, and the players in the front are going to be hindered. Now, this can be good for keeping a casual feel in a game. However, it can also ruin the competitiveness. For example, I think most of us have played a game of Mario Kart. Player in first place is a bit too competitive, and they get upset when they're constantly getting hit by blue shells, and they're constantly getting bad items, and really just making the game completely unfair for a player that might be more skilled than the rest. Now, obviously in a party game like Mario Kart, this isn't a huge issue, but in more competitive games, it can be a problem. You don't want games to drag on forever, and if you have this constant rebalancing, then no players can really get ahead and no players can win. So in order to keep your game engaging and fun, you need a balance of these two loops to keep the game fun for lower level players while still being competitive at the high level. Basically, you want to reward high level players for doing well and give a little bit of a helping hand for less skilled players so they feel like they have a fair chance. And we can kind of graph these feedback loops too. If we look here, this would be the graph of a positive feedback loop. As we can see, it kind of just goes up and up and up. As every time somebody gets stronger, they get more resources to do even better, right? So the graph goes up like this. If we look at a negative feedback loop, however, you can see this kind of sine wave effect where one player is getting ahead and then it rebalances to the middle, and then the other player is getting ahead and then it rebalances back to the middle, and this goes on forever. So all of that said, how does this apply to Void Rush, my game? Now before we get into that, I just want to say a couple things for the channel. First of all, if you haven't joined the Discord yet, there's tons of cool people talking about programming and Minecraft and Bucket and really anything else. It's also soon to become the second best place besides the Mindstorm Discord to learn about how to use Mindstorm. Second, another big announcement, we now have channel memberships, which is just an extra way of supporting the project if you want. Now, none of my content will be behind paywalls, there's no exclusive videos or anything, everything's going to remain free on my channel, but if you're looking for an extra way to support, channel memberships are a great way to help me out. With all that said, let's get back to the video. So what is the problem in Void Rush? Now, it's basically what I described before in my example with the coins. In the game, players can buy upgrades with Void Ore, but if they die, they lose Void Ore. And this kind of leads to an issue where the players who are getting lots of Void Ore are having more health, they're getting more upgrades, they're getting more powerful, which allows them to get even more Void Ore and more powerful upgrades, and so on. That sounds like a positive feedback loop to me. The graph of Void Rush right now would look something like this, where the top end players are just doing so ridiculously well that no one can really compete with them, and the game is kind of decided in the first 2 or 3 minutes when the top players establish their Void Ore and get some upgrades, and by that time the game is basically over for everyone else. And on the flip side of this, we have the positive feedback loop of players doing worse and worse and worse. So really, it's a double issue, because not only is there this feedback loop of top level players getting even stronger, there's also this positive feedback loop where the bottom players are just getting pushed down and down and down because they keep losing Void Ore and they can't buy more upgrades. So we have to find a way to fix this issue without ruining the competitiveness of the game, because I don't want this to be a party game like Mario Kart. I don't want it to be where players are basically always just fighting for the middle ground and nobody can really ever get ahead or win the game. I want it to be a competitive game. So we're going to have to use a mix of positive and negative feedback loops. So we're going to have to find a way to kind of balance out this positive feedback loop, and also it kind of limits the way you can play the game, because basically if you're not rushing center and getting the Void Ore and getting upgrades and progressing like that, then you are left in the dust. Now obviously Void Ore is a huge part of this game and the core mechanic of the game is around retrieving it, but we don't want it to be the only way that players can do that. We don't want it to be the only way that players can impact the game. So rebalancing this, we basically want to keep the positive feedback loop of players who are stronger getting stronger, but we want to kind of remove or mitigate the one where weaker players get weaker. We may want to tone down the stronger get stronger, but at the same time we do need the game to push in a direction, otherwise it'll never end. So how am I actually going to solve this issue? I've come up with a system that I think is going to help. It's not final yet. I would love to hear all of your feedback on it. Essentially, every team would now have a shield. So I've removed Void Ore stealing, so you can't take other people's Void Ore anymore, because I did some playtests with that and it kind of just turned into players would go to the island to get Void Ore, and while they're at the island, 10 players would show up, steal all their Void Ore, and they would die instantly, which is not fun for anyone. So I removed Void Ore stealing completely. But this system, every team would have a shield, and the shield would be like a regenerating health bar, and players can attack teams' NPCs to deal damage to that shield. And this does two things. First of all, when the shield is broken, one of two things happens. Now, I'm not sure yet which one I want to do. do. Either I'm just going to make it take some void ore off the thing, not give it to the player who broke the shield, but just take it off that team. So it'll be like, think of Sekiro when you're fighting a boss and you have that stamina meter, and once you break their stamina meter, you can do an execution on them, which does huge damage to their health. Or the second option, I will have it increase the void ore it takes when respawning for a certain amount of time. So say blue team shield gets broken, it now costs the blue team maybe 3 times as much void ore to respawn for a minute or something like that. I'm not sure which system I want to go with yet. I'm going to probably test them both, and whichever one works better I'll keep, but that's the idea. Now the second thing that happens when you attack a shield, you get a second currency. Now I don't know what to call it yet. If you have any ideas, leave them in the comments, that'd be super helpful. But essentially what these would do is instead of buying upgrades, so upgrades are kind of split into 2. There's the upgrades like weapons, armor, pickaxes for mining void ore and stuff like that, so the like material things, and then there's the void powers. Now the void powers would still be purchased with void power. I'm not getting rid of that mechanic, but the rest of the upgrades would now be purchased with this new currency. So essentially, in order to encourage another way of play, players can also choose to attack other people's islands to get this currency to get upgrades. And this kind of helps players who are on the lower end because it will allow them to have another way of playing that doesn't involve directly conflicting with the top players. So if the top players are all trying to get void ore from the middle and they're all fighting in the middle, then another player can bridge over to their base, damage their shield, and get some of the new currency to get upgrades and get maybe a bit stronger, and then they can go to center and start trying to take void ore. Think of it like the diamond generators in Bed Wars, where players kind of have 2 ways of playing. They can either go for the diamonds and get team upgrades and kind of build slowly like that on their own, or they can rush other people, or they can rush center. There's a whole bunch of different ways of playing, and that's what I'm trying to introduce in this game, is a couple more ways of playing. And I think this will help because, again, it balances out that issue where players who are at the top are always in direct competition with the players who are at the bottom. And another thing is I think it'll make the game a little bit more challenging because players will constantly have to think about guarding their base. And because of the shield, they'll always have enough time to get back to their base to stop the damage to it. However, if they're out in a fight or they're trying to control middle to get the void ore, they might not have time to go back and they'll end up losing void ore. Overall, I think the system should help a lot in managing players' interactions with each other and trying to keep the stronger players from just absolutely destroying the weaker players. But at the same time, we still leave in that positive feedback loop where stronger players get stronger. I'm not sure if I'm going to need systems to tone this down even more, but I think it might be okay because now the strong players, while still having that positive feedback loop, have a bit more to focus on as they have to defend their base as well. And also, again, the weaker players have a way to get stronger without directly competing with the top level players. So about 3 weeks ago, I ran the very first playtest for my minigame server, and as you might expect, it went pretty terribly. Servers crashed, things broke, it was just a general nightmare. As anyone who was there can tell you, there was more sitting around waiting for things to be fixed than there was actual playtesting. So overall, about as well as you would expect a first playtest to go. Now from this, I was able to gather some data and fix a few bugs, but one critical oversight on my part almost made the entire thing useless. Welcome back to the devlog, everyone. Today we're going to be talking about how my lack of a central logging system almost ruined my playtest. For those who don't know, logging is a way to track and record everything that happens while a piece of software is running. For this case, logging is required to understand the inner workings of the servers and plugins running the network. Logging is not as exciting as other systems, as it's never really shown to the end user. However, it's still extremely important because without it, you end up having no insight into your software while it's running. Now, in the case of most Minecraft servers, the default logging option works just fine. It just takes all of the logs, puts them into a file, and you can read them whenever you want. There's timestamps, it's all good. Works pretty well for most servers. However, in my case, I'm running a network, so there are many different servers across multiple Kubernetes pods. So not only are all the logs in different places, but the log files themselves are ephemeral. This means that just logging everything into a file won't work, because not only are there too many servers to get logs from, but log files are also destroyed when the pods shut down. So to tackle this problem, we're going to need a more professional solution. In short, we need a central logging system, or a log aggregator. What a central logger does is it takes all the logs from all the different places in real time and puts them in one place. It also handles many other things like organization, error reporting and alerts, and other general features that you might want when dealing with a large quantity of log data. Now there's a few enterprise solutions such as Splunk, but for my use case it's a bit too over the top. I need a solution that I can self-host and is preferably open source. This is where Greylog comes in. I was able to find a few different options for logging solutions that match my criteria, but overall the one I decided to go with was Greylog. Greylog is good because not only does it allow you to self-host, but it also has an enterprise version. This means if I ever start needing logging at a higher scale, I won't have to change change my entire underlying logging system. Greylog also allows the use of message brokers like RabbitMQ to deliver logs, meaning I can just use my current system with RabbitMQ for logging as well. So now that I have software to handle log data and a way to send the logs, I need a way to actually collect them. Because Greylog allows us to use RabbitMQ, all I have to do is write a small plugin that captures logs from the console and sends them via RabbitMQ to Greylog. And just like that, we now have a full central logging system. Now right now, it only logs messages on the servers. It doesn't log anything from Kubernetes or the pods themselves, but in future this could be easily expanded because all we have to do is pipe more data into Greylog through RabbitMQ and it will automatically organize it, categorize it, and make sure that everything is properly sorted. This is also super useful for live DevOps as well, because I can easily find errors and debug issues while the servers are running, because I know exactly when and where errors are happening. Greylog also allows me to set alerts so that if something is going wrong more than usual, or if there are many errors coming from a certain part of code, it will ping me and let me know so I can fix that. So now that I have a logging system in place, running playtests will be far more useful because I'll have proper insight into what went wrong rather than just guessing in the dark at what happened. There comes a time in every development project where you've learned enough to look back at the code you've written at the beginning and say, how did this ever work? How did this massive pile of spaghetti ever function? And how on earth am I going to scale this into bigger things? When you reach this point, there's pretty much only two options. Either you can scrap the whole project and move on to something new, or you can do a full rewrite. I reached this problem with Gearflux about 3 months ago. I looked back at the code I'd written in the start and found absolute spaghetti, nothing scalable and nothing I could continue to work with. But I'm not quite ready to be done with this project yet, so I decided to do a full rewrite. In this video, I'm going to talk about 4 different things that I've done to improve Gearflux systems and hopefully build a more scalable future for the project. But before we get into that, I just want to say a huge thank you to my channel members who make this all possible. If you're interested in becoming a member, click the join button below the video. So as many of you know, Gearflux uses a dynamic server scaling system. This means that it spins up and down servers according to the load. Now my original system for this was far less than ideal. It only supported one proxy and basically routed all the traffic through one singular point. The problem with this is that not only do you have a single point of failure, but it also prevents the program from being scalable because you can only make one machine so powerful, and because it's not distributed, that machine has to process all of the connections. This central point of failure was the proxy. It was basically handling everything from server connections to general Minecraft protocol stuff to spinning up and down servers and matchmaking. Now, as I said before, the problem with this is that there's one single point of failure. Basically, if this proxy goes down, the entire network goes down. And also it's not scalable because those systems can't be distributed across a fleet of different machines. Because of this, it means that there's a limit to how far we can scale the server, because the machine running the proxy directly influences the performance of the server, and you can only make one machine so powerful. So we have to find a way to distribute these systems across many different machines and make them scalable. Now, luckily for me, I'm not the first person in the world to want to do something like this, and there's an architecture people use for this kind of system. It's called microservices. Microservices are essentially where you build a whole bunch of different applications that all run individually, and then you connect them together with something like gRPC or GraphQL. Usually the services running inside this kind of architecture are containerized, meaning they'll use something like Docker, which again is useful because we're already using Docker for our servers, and it also means that we can distribute this with Kubernetes, and we don't have to manage container orchestration ourselves. With my newfound knowledge of microservices, I decided to split the Gearflux systems into their own microservice, a server orchestrator, which would manage the allocation of servers and proxies, and the matchmaking service, which would handle player matchmaking. And yes, you heard me right, proxies. Because the system is split into many different microservices, none of the matchmaking or server orchestration code happens on that singular proxy anymore, which means the only thing that the proxy does is handle player connections. Because of this, we can now have theoretically as many proxies as we want, because all we need to do is connect all the servers to all the proxies, and it doesn't matter what proxy you're connected to, because it'll always route you to the right backend server. This whole system allows for far more scalability, because the only thing that we'd need to do if more players connected is spin up more instances of the proxy or the servers. Essentially, everything is distributed, so it's infinitely horizontally scalable. It also means that the proxies aren't responsible for handling all of these calculations with the matchmaking and the server orchestration anymore, which means they can be lighter. Which brings us into our next issue, server performance. Pretty much anyone in the Minecraft community will tell you how horribly optimized servers are. Even the cutting-edge technology like paper still requires gigabytes upon gigabytes of memory and hugely powerful CPUs to support many players. And even with massively powerful machines, player counts usually cap out at around 300. Now, this is okay because we have a distributed system, but it's also a huge race of resources to process all of this extra stuff that we don't really need. For example, if we're just running a lobby server, there's not really much point to have mob AI or terrain frame generation, or any of that extra code taking up extra memory. So what's the solution to this? Well, the answer comes in the form of new Minecraft server software called Mindstorm. Now, I don't really know if server software is the right word for it. It's more like a framework for building servers. Mindstorm comes with very little functionality by default. The whole point is you build everything yourself. This means there's no extra overhead because if you don't need a system, you simply don't implement it. It's also a far nicer API than the Bucket API, which is pretty janky from all the years of forks and clones and rewrites and everything else that got shoved onto this ancient API. Mindstorm is a much more modern, cleaner way to work with Minecraft server code. And after seeing the stuff that the Mindstorm community has been able to create, I was pretty convinced that Mindstorm would be the right choice for my server. Now, like I said before, performance is a big deal, and fortunately, Mindstorm helps us significantly there too, as not only is it far more lightweight because of the extra overhead that doesn't have to happen, because you don't have all these bloat systems that you're not actually using, it's also just a far more optimized program. This is mainly due to its efficient use of multi-threading. Well, that's our servers taken care of, that's all cleaned up and optimized, but how about the proxies? What can we do there? Well, this one was a bit tougher, because the proxy I'm using is called Velocity, and it is quite optimized, and it is written from the ground up by the same developers who make Paper. However, I thought we could do better, because I don't really need very many features for the proxy, just a basic thing that can handle server connections and route players. I set out to search for something that was better. Luckily for me, a member of my Discord kindly recommended a new proxy written in Golang called Gate. Not only is this proxy much faster because it's written in Go, it also requires far less resources. Just for comparison, the original Velocity proxy with one player on it took about 1,000 to 1,200 megabytes of memory. The new proxy takes just 11. That's right, 11 megabytes. That's over 100 times less memory. That pretty much means that with the same amount of memory, I can run 99 more proxies, which is obviously a massive improvement. Go is also an interesting language that I've been wanting to learn, so this is a perfect opportunity to dive into it. So overall, between Mindstorm and Gate, the new system uses far less resources. Before, a game server or a lobby server would take about a gigabyte to a gigabyte and a half of memory. Now it only takes around 400, and the proxy would take about a gigabyte of memory. Now only takes 11 megabytes. Obviously, these are huge performance improvements. Not only that, but the startup time for the old game servers with Paper was around 30 seconds. The new ones with Mindstorm is about 500 milliseconds. Now the final thing I want to talk about is Void Rush. Void Rush has had many iterations over the course of its development. However, I'm not really happy with it in its current state, so I've decided to redesign most of the systems to create something that kind of resembles the original game, but in practice has many differences. For starters, I don't really see any reason why the game should be played in the sky. Originally, I had liked the idea of a Bed Wars style map, but I think honestly it's just holding the game back, and I would rather move to more land-based ground maps. The next change is I'm going to remove void traders. Personally, I don't think they add much to the game, and I think there would be better methods of doing the same thing. Instead of void traders, I would have randomly spawning cash out points that you have to defend for a certain amount of time to cash out your void ore, similar to something like the finals. Instead of having a void trader that every player owns, there would be a random shop that pops up around the map where you can trade void ore for powers. I would also remove the soul shard system, as I don't think it adds anything to the game and just creates confusion. I would also remove the elimination system from the game, because I don't think that it's very much fun to have teams get eliminated. Rather than that, I would have a placing system where teams with the most void ore would get the higher spots. Again, similar to something like the finals. All of these changes I think will help make the game stand out more and make it a bit more unique, as well as more fun to play, as it should remove some of the feedback loops and the issues with the current game. Now, the reason you haven't seen much progress from me over the past few months is honestly just due to these changes. Basically, I've had to re-implement everything that I've written so far in these new systems. Now, while some of the code can just be copied over, most of it I want to refactor because behind the scenes, the structure of the code is quite poor. And as I learn new things, I want to start implementing them to make my systems cleaner and more professional. One of the hardest parts of any project is doing all the behind the scenes work. The work that's rarely noticed by the end user. A saying that seems to hold true with most software projects is 90% of the work happens in the last 10% of the project. Pouring hours of effort into a system that no user will ever see is the worst feeling and leads to a severe lack of motivation. Despite all of this, these hidden components are required for a functioning system. Today, we're going to be talking about one such system I've been working on developing over the past few weeks. So with that said, let's dive into the workings of the Gearflux permission system. But before we do that, I just want to say a huge thank you to the channel members. If you like what I do and are interested in becoming a member, click the join button below the video. So why do we even need a permission system? While a permission system might not be the most interesting feature to implement, it's still a critical part of a Minecraft server. Managing player permissions is vital, as without a proper permission system, it is extremely difficult to set up effective moderation. Normally in a project like this, I would just use LuckPerms, as it's a fantastic project and has pretty much everything you need when it comes to a permission system. However, those of you who watched the last video will know that I'm no longer using Paper or Spigot. In short, I'm now using a software called Mindstorm, If you want to learn more about what Mindstorm is and why I decided to switch, check out the last video. There should be a card somewhere in the top right. Unfortunately, there's no Mindstorm support for luck perms. Mindstorm does have a built-in permission system, but because our server is distributed, the permission system has to sync across many different server instances and even proxies. For this reason, I decided that creating my own permission system would be the best option. So where do we even start with creating a permission system? How does it even work? Well, you can think of it as a big tree, where every leaf is a permission node and every branch is a connection. These nodes can be anything, for example admin or mod or player or anything else. Then, each of these leaves has a branch to other leaves. For example, we could have admin.commands, where the first permission node would be admin, and then under that, we'd have another one called commands. This is called a hierarchical permission system. Every permission node can have a tree of permissions under it. This hierarchical method allows us to organize permissions in a way that makes sense. For example, if we have a top-level role called admin, we might want many different permissions underneath that, and even other permissions with permissions under them. Now that we have a concept for this system, how can we go about implementing it? Well, remember that this system has to sync across many different server instances, so for that reason, we're going to need a database. On the topic of databases, have you ever wanted to learn how to build your own? Well, now you can with CodeCrafters. CodeCrafters is a platform designed to elevate your programming skills through advanced challenges, like building a database from scratch. With support for a wide range of languages, you can explore and master both familiar and new technologies. Plus, you can collaborate with a vibrant community of developers. It's free to sign up, and if you decide to upgrade, you get 40% off with my link in the description. Whether you're an experienced coder or just starting out, CodeCrafters offers the perfect hands-on approach to learning. If that sounds interesting to you, check it out with the link in the description. Now let's get back to the video. So, we're going to need a database to store our permissions. But the question is, which one? With so many different options and so many different styles of data storage, we have to choose the model that best suits our needs. There are many different types of database to choose from, but the three options we're going to look at here are relational databases, NoSQL databases, and finally graph databases, which are a form of NoSQL database. These three options make the most sense for how we're going to be storing our data. Let's start with understanding a bit more about each of these database architectures. Relational databases are the most common. They work by storing data in columns and rows. You access the data with SQL or SQL, which stands for Structured Query Language. These kinds of relational databases are best used when the data you're working with has well-defined relationships. However, they are not as suitable for more fluid data. A big advantage, however, is the fact that these databases have been around for 20+ years and have a huge amount of resources behind them. For example, the most popular relational database, MySQL, was developed in 1995 and has nearly 30 years of tested high-volume use to ensure its reliability. The next database type is NoSQL databases. As the title suggests, these databases do not use SQL. There are many types of NoSQL database, such as key-value stores like Redis, document databases like MongoDB, and graph databases such as Neo4j. Key-value databases like Redis are often used for storing ephemeral data, as well as data that needs to be updated and accessed very quickly. Document databases tend to be best for unstructured data, projects where data might come in many different formats, or where there's no relationship between data. On the other end of that extreme, there are graph databases. Graph databases are NoSQL databases that store data through relationships, similar to relational databases. That being said, they do not relate data in quite the same way that databases like MySQL and Postgres do. Rather than columns and rows, graph databases use nodes and edges, where nodes are the data itself and edges are how the data relates. These databases are best used for projects where the data you're storing has highly complex relationships. So now that we understand all of these different options for modeling our data, we can decide on what database is best for Gearflux. After considering all the options, I decided that a NoSQL database would be the best choice, because we're going to be storing a wide variety of different data, from permissions to ranks to player statistics, and even other things. But the question remains, which database? Well, I'm already using Redis for a number of the server orchestration systems, so it might make sense to use that for everything else as well. However, Redis is designed to be an extremely fast ephemeral database, and while you can make it persistent, that's not what it's built for. Graph databases might be a good choice. However, I don't think that Gearflux needs that level of relational complexity, so that leaves us with one choice left: document databases. But now the question is, which one? There are many good options, but the one I went with is MongoDB. There are a few reasons I chose Mongo. The first is that it's by far the most popular and widely used document database. It also has been around for quite a while and is used in production for many large-scale applications. The second reason is it probably has the best developer experience when it comes to setting up a database fast. All you have to do is go to the website, make an account, and boom, you get a free MongoDB cluster that remains free as long as you're under 500 megabytes of data. Not only that, but Mongo Compass is a fantastic GUI tool for managing and visualizing the data, which can be somewhat more cumbersome in other databases, which rely mostly on third-party tools. The fact that MongoDB has its own free tool, and that it's quite good, is a huge help. The final reason is I've worked with a few SQL databases in the past, and I was eager to learn something new. Next, let's take a look at the way MongoDB handles some of its core operations, as it's one of the defining features, and it's important to understand when working with it. When we're talking about databases, you might hear about something called CRUD. CRUD is an acronym that stands for Create, Read, Update, Delete. These are the 4 basic operations that can be performed in any database. But for this explanation, we can further abstract these concepts into simply read and write operations. Each of these operations has a different cost. Cost is just how much time it takes to complete the different operation. The cheapest operation you can perform on a database is a read. The main reason for this is that databases are highly optimized to retrieve vast amounts of information very quickly. Another reason is that no concurrency conflicts need to be handled, because no data is being changed. Write operations, on the other hand, are much more expensive. This is caused by a few things. The data not only has to be written once, but indexes might also need to be updated as well. Indexes are a bit of software magic that creates a structure that allows the database to access data more efficiently. Essentially, they work like a book's index, allowing the system to quickly find the location of specific data. Another reason write operations are slower is because of concurrency handling. Let's say, for example, we have a video, like the one that you're watching right now. Let's say you click the like button on the video. At the same time, another person watching the same video clicks the like button. The database has now received 2 write operations at the same time. So how can it handle this? First, let's look at the way MySQL, more specifically InnoDB, which is the storage system MySQL uses, handles this problem. Because it is physically impossible to have both operations received at the same time, because you can always have a smaller division of time. One of the operations will be handled a split second before the other. When this happens, the database will lock the value so it cannot be changed until the first write operation has been completed. If any more write operations come in while the first request is being processed, the database will queue them up and execute them sequentially following the same locking principle. This process is called concurrency control. However, it's not the only way to handle the issue of concurrency writes in databases. MongoDB handles this problem a bit differently, with something called optimistic concurrency control, or OCC for short. OCC works on the principle that write conflicts are few and far between, so it does not use any kind of locking system. That being said, OCC still has the functionality to deal with write conflicts if they occur. Let's go back to our example with the video and the light count. Let's say we have a document in our MongoDB database that represents the video. In MongoDB, our documents are stored as BSON, which is kind of like JSON, BSON meaning binary JSON. So let's say it looks something like this. We have our video ID, our title, and our light count. Now, just like before, we're going to send 2 requests to update the light count at the exact same time. Here's what happens. Operation A starts and increases the light count from 10 to 11. At the same time, Operation B starts and also increases the light count from 10 to 11. Then, Operation A is committed, updating the light count in the database to 11. A microsecond later, Operation B attempts to commit. However, before it does, it detects that the document has been modified since it made a copy to write on. The behavior that happens next is entirely controlled by the developer. Either the operation can retry with the updated copy of the document, or it can simply be cancelled. It's also worth noting that every write operation is atomic, meaning it either writes the full value of the document or writes nothing at all. This prevents cases where for some reason the writing could be interrupted before it can be completed. If the documents were not atomic, it would leave half-written values and could lead to data corruption. This method of OCC can be faster, especially in scenarios where the write conflicts are infrequent. However, it can make things a bit more complex when dealing with the rare conflicts that do happen. It is worth noting that MySQL also supports OCC for handling certain concurrency scenarios. So now that we have our database and we understand some of the core concepts behind its design, how can we use this for the permission system? Well, another reason I chose MongoDB specifically is because it allows us to use graph queries. These are not quite as complex as true graph databases, but they can be a huge help in optimizing our permission lookups. Why is that, you ask? Well, remember that our permission system is stored in trees. These trees are just graphs. This means that whenever we want to query a permission, we can use MongoDB's graph lookup feature to optimally traverse our permission tree and retrieve the information we need. So there we have it, a fully functioning permission system, properly synced across our network. This system might not be the most interesting, but I did enjoy working on it quite a bit, as I was forced to learn a lot about databases and how they function. I didn't even begin to scratch the surface of all there is to be learned when it comes to working with databases. But that being said, I have learned a lot, and I hope by watching this video you have too. Let me know if you found any of this interesting in the comments below. Also, give the video a like if you enjoyed it, and consider subscribing to see more content like this. With that, thank you everybody for watching, and I hope you have an excellent rest of your day.